So, um, imagine you're just walking through a modern airport, right? Like in the 10 minutes it takes you to grab your coffee, shuffle through the security line, and, finally find your gate.
You've probably been captured by, what, dozens of cameras?
Oh, easily dozens, maybe hundreds. I mean, you're on the coffee shop security feed, the TSA's overhead monitors, those terminal flow sensors.
And probably in the background of like 3 different people's vlog posts.
Exactly. And if you multiply your 10-minute walk by every person in every airport, shopping mall, traffic intersection, and hospital on Earth, well, we're generating just an absolute ocean of video data every single second of the day.
Yeah, it's a staggering amount.
It really is. But collecting all that footage isn't actually the hard part anymore. Storage is incredibly cheap, and lenses are practically free. The real bottleneck we're facing right now is human attention.
Right, because it's a mathematical impossibility for humans to review even a fraction of it. You could hire half the planet to watch the other half, and you would still fall wildly behind.
Which brings us to the entire reason for this deep dive. Today we're exploring a really fascinating source text titled AI Video Analysis, Recognition, Summarization, and Crowd Safety. And our mission for you today is to shortcut you to being perfectly well informed on how AI is stepping in to solve this impossible bottleneck.
It's a very necessary intervention.
Yeah, we're going to explore exactly how AI takes this endless raw footage and turns it into organized, actionable insight without, drowning you in impenetrable computer science jargon.
Because the stakes here are actually surprisingly high. I mean, think about it. If you have 40 hours of continuous security video from a massive factory floor, there might only be, say, 3 or 4 seconds in that entire recording that actually matter.
Right, out of 40 hours.
Exactly. It could be a sudden safety hazard, or a machine malfunctioning, or maybe a crowd pattern shifting dangerously at a public event. The AI's entire job is to watch that endless stream of the mundane and answer a few core questions. What happened? Where did it happen in the frame? When did it start and stop? And most importantly, does someone need to act on it right now?
Okay, let's unpack this, because this is where my brain immediately hit a roadblock when I was reading the source material. It sounds simple enough until you realize how a computer actually looks at a video,
No,
because it is absolutely nothing like human vision.
no, not at all.
We just open our eyes and our brains instantly understand the context of the world. But in AI, it has to build that understanding from scratch, right? Like pixel by blind pixel.
Yeah, that's the foundational hurdle of computer vision. To build that understanding, the AI relies on 2 completely separate building blocks. You've got spatial information and you've got temporal information. So spatial information is basically assessing what is in the frame and where it's located at a frozen point in time. The AI looks at a single static image and uses something called 2D convolutional neural networks, or CNNs.
I want to pause there.
Yeah.
Because whenever I read convolutional neural network, my eyes just completely glaze over.
That's completely fair.
But the source actually broke it down really well. It's not like the AI intrinsically knows what a door is, right? It's scanning the image for edges.
Precisely.
It finds a vertical line. It notices a shift in the color gradient, identifies a geometric shape, and then, through millions of examples, it eventually associates that specific arrangement of pixels with the label door.
That's a really great way to visualize it. It's just assessing the visual layout of static shapes, so it spots the pixel arrangement of a person near the pixel arrangement of a bag on the floor.
But see, if the AI knows there's a person in a bag, my first thought was, isn't that enough to know what's going on? And it turns out it's really not.
No, it lacks context.
Right. Imagine you're looking at a single, frozen spatial frame of a person leaning forward at a dramatic 45-degree angle. Just looking at that one image is completely useless. I mean, are they leaning forward to stretch before a morning jog? Or are they mid-fall and about 1/10 of a second away from hitting the concrete?
You absolutely need the temporal sequence to know the truth,
Exactly.
which is where temporal information comes in. It provides the understanding of how the scene changes over time. Sequence and motion are what turn isolated, static shapes into actual events. I mean, standing becomes walking, walking becomes running.
Right.
So a sophisticated model has to bridge the visual appearance from the spatial data with the motion from the temporal data.
But how does it actually calculate that motion mathematically? Because it's not like there's a tiny digital brain inside just watching the screen play out.
No, definitely not. It relies on what engineers call motion signals. And there are a couple of really clever ways to extract these before the AI even bothers identifying what the objects are. The first is called optical flow.
Okay, optical flow.
Yeah, think of this like, well, Imagine throwing a handful of brightly colored leaves into a river to see how fast the water is moving and in what direction. The algorithm literally tracks the direction and speed of specific clusters of pixels as they move from one frame to the next.
Oh, wow. So if a cluster's moving rapidly to the left, the AI registers a strong leftward trajectory.
Exactly. And the second method the source mentioned is frame differencing, which honestly is incredibly elegant.
It sounded like a magic trick to me. It takes frame A, lays it directly over frame B, and simply subtracts any pixels that stayed the same.
How'd you?
So if you have an empty hallway, nothing changes between frames, and the AI sees nothing. But if the person runs through, everything in the background cancels out, and only the pixels making up the person register as active.
And the beauty of frame differencing is how computationally cheap it is. I mean, even before the AI's complex networks fully recognize that those moving pixels represent a human being, just sudden motion alone is a massive clue.
Right, just the change itself.
Yeah. If an area is normally completely static, like, say, a secure vault door at midnight, and suddenly there's a massive spike in optical flow, the system immediately knows an anomaly is occurring.
And it isn't just looking at the video in a vacuum either. The source highlights that AI uses multimodal context. It pulls in audio, like a loud crash or a crowd cheering.
Yeah, audio is huge.
And it pulls in metadata too, right? Like timestamps, camera locations, or even changes in a sports broadcast scoreboard.
Because context entirely dictates meaning. I mean, a person running through a park on a sunny Saturday afternoon means one thing. A person running through a bank lobby at 2 in the morning while a high-pitched audio frequency is blaring.
That means something entirely different.
Exactly. The multimodal approach is what tethers those moving pixels to the reality of the situation.
So, if the AI now understands movement across frames like, it knows their objects, it knows they're moving, and it has the audio context, how does it actually attach a definitive label to what it's seeing? How does it graduate from seeing fast-moving pixels to definitively stating, this is a person running?
This leads us to a massive distinction in the research, which is the difference between action recognition and activity detection.
Right.
Conflating those two is a really common mistake, but they are vastly different tasks. Action recognition is actually the simpler of the two. This is the scenario where you hand the AI a perfectly trimmed, tightly focused 3-second video clip and you ask it, what is the primary action happening here?
Okay.
The clip is already isolated around the event. The AI just has to classify it. It labels the clip as waving or eating or jumping.
You know, the way I processed this while reading the source was by thinking about language. To me, action recognition is like successfully reading a single word on a flashcard.
Oh, I like that.
Right. But activity detection, on the other hand, is like being handed a 1,000-page novel and being told to find one specific, highly important sentence hidden somewhere inside it. It's just a completely different scale of problem.
The novel analogy is perfect. Activity detection requires the AI to sift through a massive, continuous video stream. It isn't just asking, what is this? It has to answer, what happened, where did it happen in the frame, and exactly when did it start and stop. Real-world surveillance footage is incredibly messy.
Yeah, it's not perfectly framed.
Right. Events don't happen neatly in the center of the frame in convenient 3-second intervals.
So if I'm looking for a specific sentence in a book, I skim. I read the first sentence of a paragraph to see if I'm in the right ballpark. How does the AI hunt for that sentence? Because scanning every single pixel of every single frame of a 1,000-page novel sounds computationally crushing.
Oh, it is crushing, which is why researchers had to develop specific search strategies. One of the brute force methods is called sliding windows. Imagine taking a physical piece of cardboard, cutting a rectangular slit in it that only reveals 3 seconds of video, and dragging that slit slowly across a massive timeline of footage.
Just relentlessly grinding through the footage.
Yeah. The AI analyzes minutes 1 through 3, then shifts slightly to analyze minutes 2 through 4, continuously making predictions for each overlapping segment.
But that still sounds incredibly heavy for a computer to process.
It takes massive server power. So a much smarter, modern approach uses temporal action proposals. Instead of treating every single second of the video as equally important, the AI does a rapid, lightweight skim first.
So it looks for those spikes in optical flow or frame differencing we talked about earlier.
Exactly. Once it finds a region where something seems to be happening, it flags it as a proposal. Only then does it bring in the heavy, complex neural networks to do boundary detection and estimate the exact millisecond the action actually starts and ends.
But because finding that one sentence in the novel is so exhausting, even for an advanced AI, We ultimately need the system to do the heavy lifting for us and just, hand us the Cliff Notes.
Absolutely.
If I have a 12-hour recording of a loading dock, I do not want to watch the 400 times the wind blew a tarp around. I want the TLDR of the video. Which brings us to the science of video summarization.
And summarization is arguably the most practical application we are discussing today. Whether someone is reviewing a 2-hour corporate meeting, a whole day of security footage, or a 3-hour football game, they usually only need the 5 minutes of actual consequence.
Right.
But the way the AI creates that summary drastically changes the final product. The simplest, oldest method is keyframe summarization.
That's where it just grabs still images, right? Kind of like a comic book.
Essentially, yes.
Yeah.
It selects representative still frames. In a corporate meeting, it might pull one shot of the speaker, one shot of a new PowerPoint slide, and one shot of the final whiteboard notes. It gives you a quick visual preview, like a thumbnail gallery, but the glaring limitation is that still images completely strip away motion and nuance.
Yeah, I mean, you can't summarize a massive football game with a still photo of a quarterback releasing the ball. You have to know if the ball was actually caught or intercepted.
Exactly, which is why the field has largely moved toward video skims. These are short, dynamically edited versions of the original video that preserve the motion, the pacing, and the sound. They're actual moving highlights.
Okay, that makes sense.
But within the creation of video skims, there is a fundamental philosophical split. Extractive versus generative summarization. Extractive summarization is straightforward. It selects real, untouched clips from the original video and simply stitches them together.
Right.
Generative summarization is much more complex. It actually attempts to create a completely new visual narrative from the source material.
Now, here's where it gets really interesting and honestly a little bit concerning. When I read about that split, it hit me. Extract is like watching a highlight reel on ESPN. You can trust it because those exact pixels happened in reality.
Yes.
But generative is like a friend retelling you a story they saw happen at a bar. It might be a smoother, more polished story, but generative AI models don't really know what the truth is. They just predict the next most likely arrangement of pixels based on their training data. So your generative summary might hallucinate visual details that didn't actually occur in the original footage.
The risk of hallucination in video is a massive concern. If you are reviewing safety-related footage from an industrial accident or security footage from a bank robbery, you absolutely must rely on extractive summarization.
You cannot have an AI generating a smoother narrative of a car crash for an insurance claim.
No, the chain of evidence has to be real pixels.
But even if you use safe extractive summaries, you run into another very human problem. If a security camera detects motion at a front door 50 times in a single day, a summary that just shows 50 identical clips of different people walking through the same door is going to put the security guard to sleep.
Oh, they would tune it out within minutes. So engineers utilize reinforcement, learning to teach the AI how to be an interesting editor. Think of it like training a pet with a complex reward system.
Oh, I like that.
The AI receives positive numerical rewards for choosing clips that are not just informative, but diverse. The system learns that if it already included a 3-second clip of the front door, it shouldn't include 10 more just like it.
Okay.
It actively seeks out a different camera angle or a different type of event, ensuring the final summary actually feels comprehensive and engaging to a human viewer.
Okay, so a diverse summary is brilliant if I'm reviewing the past. Like, I come in on Monday morning, I watch the summary of the weekend. But what about the present? If I'm managing a stadium with 80,000 people in it right now, a summary doesn't help me. I need to know if a dangerous bottleneck is forming at Gate C before someone gets crushed.
Right, real-time safety.
Exactly. How does AI handle real-time chaotic environments where safety is immediately on the line?
Well, crowd analysis is notoriously difficult because it breaks a lot of the rules we've talked about. In a dense crowd, individual people block one another from the camera's view, what we call occlusion.
Right, you can't see everyone.
And small problems in a crowd escalate exponentially. So the AI isn't just trying to count heads at the gate. It is performing complex behavior monitoring. It's mapping the flow of the crowd, analyzing how people are dispersing, and searching for localized anomalies. Are 50 people suddenly running against the normal flow of traffic? Is an exit getting artificially narrowed?
The source mentioned how surprisingly difficult specific individual tasks are within a crowd, particularly fall detection. It noted that detecting a fall is tricky because, from a high overhead camera angle, a person bending down to tie their shoe or sitting down quickly on a concrete bench looks awfully similar to someone collapsing from a medical emergency.
That is entirely due to the compression of 3D space into a 2D image. The camera loses depth. The pixel vectors moving rapidly toward the ground look identical whether the person is fainting or grabbing a dropped phone.
That's wild.
That's why the AI has to rely heavily on temporal context. How long does the person stay down? Are the optical flow patterns of the people immediately surrounding them suddenly changing as they react to the person on the ground?
I have to play the skeptic for a second, though. If we have artificial intelligence tracking every single person in a massive stadium, analyzing whether they bend over to tie their shoe or run to the bathroom, how is this not a massive, creepy privacy nightmare? I mean, how do we monitor a crowd for safety without building a dystopian surveillance state?
This raises an important question, and the privacy concern is incredibly valid. But the engineers have actually solved this in a rather elegant way using a mathematical technique called density estimation. Models designed for this, they often have names like CSRNet or MCNN, don't actually track individual identities at all.
Wait, really? They are running facial recognition on the crowd.
Not at all. Drawing individual bounding boxes around 80,000 faces is computationally impossible for real-time processing anyway. Instead, they create density maps or heat maps. The AI simply learns the visual pattern of how tightly packed pixels are in a given area.
Oh, wow.
Yeah, it doesn't know or care who you are. It only calculates that the pixel mass, the physical pressure in hallway bay, is reaching a dangerous limit. It registers a glowing red hotspot on a digital map, not a database of names. You can monitor the safety of the venue perfectly well without knowing a single person's identity.
That makes so much sense. Heat maps over headshots. It's mathematically easier for the computer and infinitely better for our privacy. But, as brilliant as all this sounds, the source makes it painfully clear that deploying these AI systems out in the messy real world is fraught with challenges. It sounds flawless in a sterile laboratory, but reality breaks things.
Reality is the ultimate stress test, and the biggest hurdle engineers face is a phenomenon called domain shift.
Yes, this concept blew my mind. Think about the last time you went to a poorly lit, crowded indie music club. The source pointed out that you can train an AI model to flawlessly spot anomalies in a brightly lit, spacious airport terminal. But if you take that exact same highly trained AI and install it in that dark concert venue, it might completely fail.
It wouldn't even know where to begin.
Right. It wouldn't know how to process the shadows, the strobe lights, or the dense overlapping of people. That shift in the visual domain essentially breaks the system's understanding.
Because we have to remember, the AI doesn't actually understand the concept of a shadow or the concept of a strobe light. It only understands the mathematical pixel patterns it was trained on. When those environmental patterns shift dramatically, its confidence in what it is seeing drops to zero.
Right.
And this limitation ties directly into the hardest problem in all of video AI, the paradox of rare actions.
The paradox being that the things we most desperately want the AI to find are the things it has the least experience looking at.
Precisely. Deep learning models require massive amounts of data to learn effectively. There are millions upon millions of hours of mundane footage of people walking normally through train stations. But there is, thankfully, very little footage of actual violent fights, medical emergencies, or dangerous crowd surges.
That makes sense.
So we are asking the AI to be a flawless expert in detecting something it has barely ever seen in its training data.
It's the paradox of needing enormous data sets for the exact events you hope never happen in reality. And even if you somehow solve the domain shift and the training data problems, you still have to figure out where the AI's actual brain lives physically. The source spent a lot of time contrasting edge computing with cloud computing.
This is the major deployment decision for any organization. Cloud computing means taking all the raw video feeds and sending them over the internet to powerful remote server farms.
Okay.
You get massive computing power, and you can run huge, highly accurate models, but it requires enormous bandwidth. It adds transmission latency, which is bad for real-time safety, and sending raw video of the public offsite raises serious privacy and security concerns.
Whereas edge computing flips that entirely. If I'm worried about latency, I'd want the processing happening right where the video is shot.
That is edge deployment. The processing happens locally, right on the smart camera itself, or on a small server sitting in the venue's security room. It is incredibly fast, and because the video never actually leaves the building, it's much better for privacy.
But there's a catch, right?
Yeah, a camera hanging on a wall has very little computing power, so you have to use smaller, highly optimized models. They use stripped-down architectures, often called mobile nets, which essentially prune away unnecessary neural pathways so they can run on a cheap microchip.
So they're faster, but maybe a little less smart.
Exactly. The trade-off is they might sacrifice a tiny bit of accuracy compared to the massive cloud models.
Well, if I'm designing the system for a venue, and I know the edge camera might sacrifice a bit of accuracy, my first instinct would be to just crank the sensitivity all the way up. I'd rather the AI flag 100 false alarms than miss one real medical emergency.
You would think so, but in practice, that creates a phenomenon known as alarm fatigue. If the system's sensitivity is too high, and it sends a blaring alert to the security desk every time someone drops a heavy bag thinking it was a fall, the human operators will get incredibly annoyed.
Oh, I see.
Within a week, they will just mute the system or turn it off entirely. False positives ruin human trust. But of course, false negatives, where the system completely misses a real emergency, can cost lives.
So how do engineers actually thread that needle?
They build a layered system using confidence thresholds. The AI is programmed so that if it calculates it is only 40% sure it saw an anomaly, it doesn't sound an alarm, it just quietly logs the clip for later review.
Fart.
If it hits an 80% confidence threshold, it sends a low-level notification to a screen. But most importantly, you always maintain a human in the loop.
Right, the AI shouldn't make the final call.
Exactly. The AI is never making the final high-stakes decision on its own. Its only job is to sift through the noise and flag the most critical few seconds of video for a human being to evaluate.
So what does this all mean? We have covered massive ground today. We started with an AI blindly looking at static pixels, and we saw how it learns to combine spatial images with motion signals to actually understand the passage of time. We saw how it graduates from identifying a simple word on a flashcard to detecting complex sentences hidden in hours of chaotic footage. We explored how it acts as a highly trained editor, summarizing lengthy events while actively avoiding hallucinations. And we unpacked how it keeps stadiums safe using anonymous density heat maps, all while fighting against shifting environments and the paradox of rare events.
It really represents a profound shift in how our physical environment responds to us.
It does. The next time you were standing in a crowded airport terminal or finding your seat at a dark concert venue, you will know exactly how those invisible lenses mounted on the ceiling above you are operating. You know they aren't scanning your face or tracking your identity. They're calculating optical flow, evaluating density maps, and using frame differencing to keep the massive, complex flow of humanity moving safely.
But as advanced as everything we have discussed is, I want to leave you with a thought about where this field is quietly heading next. We briefly mentioned a concept earlier in the research called self-supervised learning.
Oh, right.
This is an approach where AI models learn the physics and rules of the world entirely from raw, unlabeled video. There are no human programmers explicitly telling it, this pixel pattern means falling down, or this pattern means running. The AI just watches millions of hours of the natural world, observing the physics of human behavior, and it learns the sequence of how events naturally unfold on its own.
It's just absorbing the raw patterns of reality.
Yes. So I want you to ponder this. If millions of cameras are constantly feeding these advanced systems the raw, unbroken sequence of human behavior, and the AI is continuously learning to anticipate what frame naturally follows the next without any human input,
Oh, wow.
how long until the AI isn't just reacting to what we do? If it truly understands the sequence of human physics, how long until it is predicting our physical actions? A sudden slip, a sharp turn, a split-second decision, seconds before our bodies even make the movement.
Now that is a thought that will stick with you the next time you look up and see a lens pointing your way. Thank you so much for joining us on this deep dive. Keep questioning the invisible technology operating around you. Keep looking for the how and the why behind the systems we build. And remember that even in a world that is constantly recording itself, true understanding is the only thing that actually matters. See you next time.